Lesson 8, Basic Derivative Rules. All right, so in this lesson, we are actually going to make things easier. It's actually going to get a lot easier um, to take derivatives now and actually take the limit of the slope of the tangent line, right? Which is the derivative. Um, so to begin with, you know what I'm going to do? Let's take the derivative like we did in the last lesson, right? Using our first principles. And let's see if we can find a pattern. But you know what? I'm actually just going to kind of throw it up there. You guys have done enough of this where you've seen it. So I'm just going to pause it, write it all in, and then you'll see it. So okay, so I wrote it in there now, taking the limit as h approaches 0 of our first principles. Yeah, and so for x squared for the derivative, we get 2x. All right, let's see if we can figure out a pattern going on here. So now for x to the power of 3, the derivative is 3x squared. So using this pattern, can we just figure out the derivative without doing any of this, right? Just looking at patterns that arise of f of x is equal to x to the 4. Well, if you kind of imagine, right, in this one, the 2 looks like it just came down out front, right? And the same with this one. Right? The 3 was in the exponent, and now the 3 is the coefficient, right? So it looks like that exponent is dropping down out front. And then what happens to the exponent afterward? So this time it was 2 to begin with, and then it was really like 1, right? So it looks like it went down by 1. Actually, and the same thing happens in this, right? So exponent drops down, and then you'd go 1 minus that to get the new exponent, right, in the derivative. So just following that logic, what we could do is we'll bring the 4 down front, right? So the derivative, f prime of x, would be equal to 4x, and then it would be 1 less than what the exponent was, so x to the 3. Man, that was a lot easier, wasn't it? And that would have been a brutal limit to take, right? Because you would have had to kind of expand that out or, do that. So this is going to make life a lot easier. So formally, this is called the power rule, right? So formally stated, it's if f of x is equal to x to the power of n, where n is a member of the real numbers, then the derivative of x is equal to, and you see where n, right, just came out front, and then the exponent is now n minus 1, right? So pretty easy now. We can take derivatives pretty quick. Okay, and we're actually, for the sake of time, we're gonna skip the proof of the power rule, and we're gonna move on to the constant multiple rule. So this one's pretty intuitive, actually. Just kind of makes sense. What this is saying, if we have g of x is equal to some constant or some coefficient in this case, times some function, then g prime of x, the derivative, would be equal to just really that constant still up front. So if it was up front to begin with, we can still imagine out front on the derivative as well. So this first one doesn't really show that, but the next one will. So let's just take the derivative of x to the power of 60, which would be almost impossible if you were doing limits, right? Let's do that with our new rule, right? So this would just be the 60 comes down. So this would be y prime would be equal to 60x and then 1 less, so that'd be 59. It's that easy, right? Okay, so now with this one, what it would be is, it's the same thing actually. So we'll say y prime is equal to, and then we can imagine this as, this is like our c value from above. Well, we'd bring the 3 down, so it'd be 5, and then the derivative of this next of f of x here would be 3x squared. But that almost kind of makes sense, right? Because when I bring the 3 down, right, do you see how I'm going to go 5 times 3 in the end to say 15? That's probably what you would have done anyway, I would think. So y prime is equal to, and then this would be 15x squared, right? So whatever you bring down is just multiplied by the number out front, effectively. Okay, the constant rule. So this is saying if f of x is actually just some number, then f prime of x is equal to 0. And this only makes sense, right? Because if I had a graph and we had some function was a constant, which would look like a straight line, wouldn't it? Right? If it was like f of x, f of x is equal to 4, right? That would be a straight line at 4. Well, what's the slope? It's 0, right? It's 0 everywhere. So the derivative would always be 0 because, yeah, it's 0 no matter what you're doing there. So that one always makes sense to me. So yeah. Now, these ones take a little bit more effort. The sum and difference rules. Sorry, no, I got ahead of myself. These ones don't take much effort at all either. So sum and difference rules just really means that if we're taking like the derivative of f plus g, right, prime, so the derivative of, two kind of functions together. So, this, they're even kind of saying just separating these things out. It's really saying that we can just take the derivative of the individual pieces, right, of the individual terms. Okay, so not much going on there. So what this does is it allows us just to do our simple little rule for 3x and 5, just like above, and then 3x squared, 5x, and 2. Just do them all individually, which is nice because it just makes it really simple. So let's do these ones. These don't take any time at all. Y prime would be equal to, and then this was 1 right there, right? So the 1 would come down. So that would be 1, so the 3 out front, so that would just be 3. And then x to the power of 0, okay, which would just really be just 3, right? Anything to the power of 0 is just 1, so didn't really need that at all. And then the derivative of just a constant, well, that's just 0, so I don't need it. So the derivative here would just be 3, okay? And just make sure this makes sense, right? I always like to think back in terms of graphing. This was, so negative 3x plus 5, that'd be a line, like this. Does it make sense that we got a 1 number? Well, yeah, because wouldn't the slope be the same everywhere on that line? So yeah, it would make sense that it's not changing. There's no value for x that's going to change anything up. It would just always have a slope of, oh shoot, I'm glad I graphed it. That made sense. Oh, it wasn't negative. I was looking at that wrong. My graph would look like this. So that's why it's 3, because it's going to be, a rise of 3, run of 1, right? That would be a slope of 3 everywhere. Okay, so that makes sense. All right, so let's do this parabola. So if we were figuring out the derivative of this, again, just one at a time, this would be, well, the 2 comes down, right? And then multiply by the 3 out front. So that would be 6x, and then 1 less, so just 6x. Okay? And then move on to the next one. This would be, well, that was 1, so it comes down as 5. And then 1 less than x, so x to the 0, so just 5, right? And then, yeah, this one, and then the last part, the derivative of negative 2, well, that's just 0. So plus 0, but we didn't really need that. So there you go. There's our derivative. Man, that's simple, isn't it? So this makes sense too, though, right? If we were figuring out now, if this was our graph, and it looks something like this, let's say, then what we just found was anywhere I want to figure out the slope, right? If it was at like 4 or something, then I could plug 4 into that, and it would give me the derivative right there. Okay, let's do this one. So usually what we're going to want to do, especially now, is rewrite this a little bit different, right? Why don't we write this as f of x is equal to 6 times x to the power of negative 8. That's going to make life a little easier. So now I can say f prime of x is equal to, and we'll stick to the same rule, right? The 8's going to come down. Okay, so maybe I'll do it in 2 steps. So it'd be like 6 times negative 8. And then x to the power of, and then just, it's still going to be subtracting, right? So this would actually be negative 9, right? It's going to get 1 less always. Okay, so we've got f prime of x is equal to negative 48, and then x to the negative 9, negative 9. So, you might want to rewrite that as negative 48 over x to the power of 9. All right, next one. Okay, so again, I'm not a big fan of leaving it as a radical. So let's write this actually as an exponent. So we'll rewrite this as y is equal to x to the power of, and then remember it's the exponent on top. So this would be like in the numerator of the fraction. So 3 over, and then it's the root on the bottom. Or sorry, 2. Sorry. So 2 and then over 3, right? The root goes in the denominator. And now we can stick to the same rules, right? So this would be y prime is equal to, the 2 over 3 comes down, so 2 over 3 x to the power of, and then we have to do the same thing, right? So this is going to be 2 over 3 minus 1, right, is what we're doing here. So in this case, like you can do this in your mind, you'd write it as 3 over 3, right? So this would end up being 2 minus 3. This would be negative 1 over 3, right? So this would be to the power of negative 1 over 3. And that's fine. You could leave it like that, but typically we don't like to have negative exponents. So I'd clean that up a bit. That would be this. That would be y is equal to, and I'd probably write it as 2 over 3, right? Keeping the 2 over 3. And then you could leave it as x to the power of 1 over 3, or 2 over 3, and then the cube root of x, right? That'd be the same thing. Now, if the question said that it should be rationalized, you might want to do that as well, right? But for now, we'll leave it as this. We'll be fine. Okay. And yeah, as a general rule, if you start with rationals as your equation, right, like something over something, end that way. And if you start with radicals, right, like we did here, your answer should be as a radical as well, right? Instead of leaving it as the fractional exponent. All right, next one says find the derivative of f of x, and this time it's with absolute values. So what I think the best strategy is going to be here is just to break this thing into its pieces. Because remember our absolute values, the way they look, right? This would be, it's going to be something like this, right? With the lines. So remember that you break it into two pieces, right? It's going to be everything above this point, right? Or everything to the right of this point and everything to the left of that point, right? So that's the idea. Let's break it into its two pieces, right? To account for like the negative version of it and the positive version of it, right? So let's do the positive version. So we'd say this is the same thing as, f of x is equal to just 4 minus 6 over 5x. And then this side would be f of x is equal to, and then negative 4 minus 6 over 5 x. All right, so what's going to be useful, though, we'll just find the derivative of both of those, right? Because that should be like the slope on this line and then the slope on this line, right? And to get a feel for this, they should be the same number, but negative, right? You would imagine being in this example. But the other thing that we're probably want to figure out is actually where it changes, right? Where like the sharp point of this is. So let's do that quickly first, even. And we'll do that just by solving when y is 0, right? So we can say, okay, that's going to happen when our y value is 0. So I'll say 0 is equal to, and you could actually do it for either one of these equations, couldn't you? You could do it for the positive version and you could do it for the negative version. So it's not going to matter which one. So I'll just do the positive version. So 4 minus 6 over 5x. Okay, so this would be negative 4 is equal to negative 6 over 5x. So keeping on going with that, you get, negative 20. And then 10 over 3 in the end, right? Okay, so that's going to be our sharp point. That's where it changes, right? So let's just keep that in mind. So now let's just take the derivative of both these sides. So f prime of x in this situation would be equal to, well, this would be 0, right? A constant. So just negative 6 over 5. And I was just taking just the derivative of this part using our rules from above. Okay. And then on this side, we've got f prime of x would be equal to, well, you know what? Let's actually expand that negative in first. So I'm going to do one more step. Let's say f of x is also equal to, this would be negative 4 plus 6 over 5x. And then we'll take the derivative of this one, right? So f prime of x would be equal to kind of what we'd expect, right? So this is 0, right? That's just that constant. And then this would just be 6 over 5 for the derivative. All right, I was expecting they'd be the same and just opposite signs, right? So now let's put this together. So now we just got to figure out though, like which part is each section, right? So is this actually the graph I have going on, or is it, is it actually something more like this, right? Which it could be. Well, what we can use to look at this, right? If our original function, if we just write it again, the absolute value of 4 minus 6 over 5x, the absolute values like that. If the like the a value out front, if this is positive, then it's kind of like our parabola rules, right? Where it would be opening up, right? Because this would always be above the y-axis in this case, right? Because it's always going to be positive. If this was negative, then it would be opening down. Okay, so since it's positive, we really do know that this section was our negative slope and this section was our positive slope, right? So this would be like the negative part and this would be the positive part, okay? So let's just write it all out now. We'd say f prime of x in total here would be negative 6 over 5, where x is less than 10 over 3. And it would be 6 over 5, where x is greater than or equal to 10 over 3. Now I said, like, this one was greater than or equal to, and this one was just less than. It actually could be the other way around, couldn't it? Because right at this point, they actually share that point, right? That they're together. You could even say is equal to on both of them, but sometimes we'll just, kind of commit it to one or the other. So not a big deal on that one. All right. Consider the function f of x is equal to that. Determine the derivative. So we haven't really done a type like this where we have brackets and then an exponent, right? So for right now, and actually this is probably even the easier way in general a lot of times, we're going to take the derivative just by, or we're going to expand it out first just so we can take the derivative like we did above, right? So, okay, we're going to determine the derivative of this. I just need to expand this part. So let's write this again. This would be f of x is equal to, and I'm just going to write it out as x minus 3 over root x times x minus 3 over root x. And if we distribute this, we would end up getting, you'd get x squared, and then combining our two well, I'll write them out. So this would be minus 3x over x squared, and then minus 3x over, square root of x, I should have said, and then plus, and then this would be 3 times 3 is 9, and then root x times root x is just x. Okay, and then I'll just collect those like terms in the middle. So we've got, oh, sorry, that should have been x squared. Thank you. So x squared, and then minus 6x over root x plus 9x. Now, if I'm going to take the derivative of this, I don't really like what's going on here, and even that x in the denominator, I'd like to get that up to the top. So again, I'm just going to get a little bit more. All right, so next line, we'll say x squared, and then, yeah, we'll change this up a bit. I'm going to write this as negative 6x, and then this bottom part, I'm going to bring this up, right? So this would be, but I'm also going to write it as a fractional exponent too. So that'd be times x to the power of negative a half, right? Negative a half. And then plus 9 times x to the negative 1. Okay? Now, this part here, we can handle this, right? This is just adding exponents for when you're multiplying. So one more row. We'll say x squared minus 6. And then this is really x to the 1, right? So quite often it's easy to kind of picture this as 2 over 2, right? Just so that we have the same denominator. So now 2 minus 1, this is really a half, right? So this would be 6 to the power of a half. Oh, 6 times x to the power of a half, rather. And then plus 9x to the negative 1. All right, it's ready. It's ready to derive. So from there, we'll take the derivative, so f prime of x, and we'll just do it with each of its parts, right? So now this would be 2x for the first one, and then minus, and if I bring the half down, like we would, right? You bring the 1/2 down times 6, that would become 3x to the power of, and then a half minus 1 would be negative a half, minus 9x to the power of negative 2. Just applying it to the last one there. Okay, the negative 1 times 9 made it negative 9. All right, there's our derivative. And we should clean that up a bit though too, right? Like I even said, we should put this back into a radical and back into the denominators again. So here, let's write this again as f prime of x is equal to 2x minus 3 over the square root of x minus 9 over x squared. And there you go. That's probably the better way to write the derivative. So this question was saying determine the derivative, and that says for what values of x is the function differentiable? Okay, so it's going to be differentiable everywhere that it exists, that the original function exists as well. So you could look up here too, right, at the beginning and say, well, we can't take the square root of a negative, so it can't be any negative numbers. Yeah, and it also can't be 0 either, can it? Because we're dividing by 0. But then you can also see if we end up with the same situation on these, which would make sense, right? That you can't take the derivative where it doesn't exist on the original function. So we'll say, and we'll just do the domains of both functions, of the original and the derivative. So we'll say the domain, or domains. We could say f of x, domain for f of x, dot dot, so it would be, and then squiggly brackets, x such that x is greater than 0, where x is a member of the real numbers, right? And just greater than, not greater than or equal to, because it can't be 0 either, right? It can't be 0, so it has to be greater than 0. And then for f prime of x, the derivative of x, then it's going to be the same thing, right? They'll be the same. X such that x is greater than 0, where x is a member of the real numbers. All right, find the equation of the tangent line to f of x at the point where x is equal to 9. So this is for the same question above, right? So let's think about what the equation of a tangent line would even be, right? So this function up there is a little bit weird. So just imagine general whatever function, right? This like random thing. And they're saying, what's the equation of the tangent line when x is equal to 9? So let's say it was like right there, okay? Let's make it go back a little bit so it's more of a, so you can see it. So let's say that was 9. Okay, so we're looking for this, right? So what we're after here is we need the slope of this line. Good news, we found the derivative, right? And then we really only need the x and the y point at that line too, right? So we can think of it this way, like if we, like y minus y1 is equal to m x minus x1, right? We have everything for a line right there. So then we could figure out that equation, right? So we just need the slope, because, well, and we also would need to figure out what the y value is when x is 9, right? So we'll have to do those two things. So let's figure out the slope. We'll do slope first. So we can say the slope would be equal to the derivative f prime at 9, right? So that's our function above, right? This was f of x there, or in that form. Okay, so f prime of 9. So that would be equal to 2 times 9 minus 3 over root 9 minus 9 over 9 squared, right? Just filling in 9 for our derivative there. So that would be equal to, in the end, there ends up being 152 over 9. So that's our slope at that point, right? So we're good there. Now what we got to do is we just need to figure out what the y value is when the x value is 9, right? We need that point right there. So next we'll solve for y when x is 9. So we'll say y is equal to 9 minus 3 over root 9 squared, right? This is just the original function. So then y ends up being 64. There, we got everything we need. We got the y value, we got the slope. So now let's just plug it into our equation there. So we'll just fill in what we know. So this would be y minus, and then y1 was 64, is equal to 152 over 9. And then x minus, and then x1 was our 9 value. And that is our equation, right? That's our equation. But we should, put this in one of the other forms typically. So let's multiply everything by 9 here, just to get rid of that denominator in the bottom, right? So I'm going to multiply this by 9, and that'd be, and this by 9. So those cancel. So we end up with 9y minus 576 is equal to 152 and then x minus 9. And then I think you guys would be okay from here, where you would just get it all to one side, and it would be 152x minus 9y minus 792. All right, on to the next one. Okay, find the point or points on the curve xy is equal to 12, where the tangent line is parallel to the line 3x plus y. Okay, so yeah, in this case, again, let's think of this, as a graph again. I always like to think in graphs. So, we want to figure out it, like, no matter what this graph is doing, right? Let's just get like a feel for it. They're saying at some point, right, we're going to have some line where our slope, right, would be parallel to this line, right? Let's say this line here, well, let's write this up. This line here would be y is equal to negative 3x, right? Well, I guess that wouldn't be right. So down through here, like through the center, right? So that would be like that line, y is equal to negative 3x, okay? And they're saying at what point for x would the tangent line, this one, be parallel to this one, okay? So, okay, what they have in common here is the same slope, right? They're going to have the same, this one will have the same slope as this one. And we know that slope is really going to be the derivative at that point. Okay, so this negative 3 is going to be an important value, right? So we can say, okay, we know that y prime is going to be equal to the slope, which is going to be equal to negative 3. Okay, so that's what we're after here. And now let's rewrite this a little bit different for our curve, right? If that was this curve up here. So we'd say y is equal to 12 over x. Okay, so that was that line. Now what I'd like to do is figure out, well, the derivative of that, right? Because the derivative would tell me what the slope was at any given point, right? So let's rewrite this now again as y is equal to 12x to the negative 1, just so we can take the derivative a little easier. So this would be y prime, the derivative would be negative 12 x to the negative 2. Okay, so there's our derivative. Well, okay, that's not too bad, right? Because we know what that's supposed to be equal to, right? So this is the general equation for the derivative, right? At any given point on that line there, right? But we know that it's supposed to be exactly equal to negative 3. So let's do that. We'll just say, okay, then y prime is equal to, we'll say is equal to negative 12x to the negative 2, which is equal to negative 3. Okay, so I'll write this a little different here. Let's write this as negative 12 over x squared is equal to negative 3. And then we're solving for x, right? Because that should tell me what point it would be. So rearranging this, we would get x squared is equal to 12 over 3 or 4. Okay. So then square root. So you might say, okay, this makes sense. This would be 2, right? So this would be the point 2 that this would happen right there. Okay. Now, the only problem is we just took the square root, right? And we know that actually when you take the square root, we have to account for the positive and the negative version. So this would be positive and negative 2, which if we make sense of this actually, this actually does make sense as well, because this graph of y is equal to 12 over x being a rational function, right? This thing would actually have two pieces to it. I didn't draw the other one. There'd be another part over here. Okay, so there'd be another point at negative 2 where this line was also parallel, right? It'd be like over here, and that makes sense, right? It'd be there and there. We expected there would be two answers, two places where that would occur, right? So now the very last thing to do here is to figure out what the points are, right? So I know the x values, but for a point we need the y value too. So we will say, okay, then when we'll do f of 2 would be equal to 12 over 2, so 6, right? And f of negative 2 would be equal to 12 over negative 2, so negative 6. Okay, so those are our y values. So now we can say, okay, our points would be, so points would be happening at 2 comma 6 and negative 2 comma 6. All right, I'm going to leave that one there, I think. So just one thing to keep an eye open for, maybe on a question, you might have one that says, how would it be worded? It would say something like, at what point in the curve does it have a horizontal tangent, right? So just be careful on those ones. So that would just be saying, at what point does it have a horizontal tangent? A little hint there, what would the derivative be at that point, at that horizontal tangent line, right? It would be 0, right? So just keep that in mind when you do these, when you run into those. So